Welcome to your first computer-integrated Plan Z e-learning experience. This is going to be a 7-part series that we will learn about the 6 different types of simple machines. These are simple machines that create movement through mechanical advantage, and together they can create complex machines, creating all sorts of extra effort or extra distance depending on how you want to arrange them. The simple machines that exist are the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. We're going to investigate all 6 of these, but today we're going to focus on the lever. Now, before we can even start talking about how the mechanics of the lever work, we must talk about the way the lever gets its power, and that is called mechanical advantage. Now, there's 2 types of mechanical advantage. There is the AMA, or the actual mechanical advantage of a system, and there is the IMA, or the ideal mechanical advantage of a system. We'll talk about those in future, but basically, both mechanical advantages are ratios. Now, if you forgot what a ratio is, it's basically just a fraction. Something over something else. Okay? The amount of puppies to the amount of fish is one type of ratio. Okay? So, for this ratio, the ratio of magnitude of resistant force and effort force, that's the actual mechanical advantage. I'm actually measuring the forces between the things. This is the actual. And for this ratio, that's the ideal. We're using the distance traveled by the effort force and the distance traveled by the resistant force. We're not actually taking the measurements of those forces, just the distances they will be traveling. And since we're not measuring the forces, we don't have to account for friction. We don't have to account for thermal loss or anything like that. And this is the ideal mechanical advantage. Okay, now let's go into those. Mechanical advantage of 4-to-1 tells us about the mechanism. If you look at this weight, it has a mechanical advantage of 1-to-1, which means that the force applied to move it is equal to the force it takes to pull it down. Now, the force repelling it, or the force resistant, as I will use F sub R, okay, is equal to the force of the effort as me lifting it up. This one, going up the inclined plane, has a 4-to-1, which means that the force of effort is not equal to the force of the resistant. In fact, it's not equal in a very certain way. And that way is to say that 4 times the resistant for every 1 effort that we put in. Now, that's a really fancy way of saying this. If you notice, this little guy right here, that little arrow, that little red arrow, that's how much force I'm applying to it. Okay. Now notice the blue arrow, how much it weighs, that's the force of gravity pulling on the object, is the same as the force if I'm just pushing it straight up. Okay. Now if I'm going up an inclined plane, that force that's pulling it down by gravity is the same, but I don't have to exert the exact same amount of force now, because I'm not going straight up. I'm now going over an inclined plane. It is now making my life 1/4 the way easier. Okay? That means 4-to-1. That means for every 1 pound of force that I use to push it is equal to 4 times the force necessary, the force that it weighs. Okay? So for every 1 pound of force I use, I could push a 4-pound object. Now, there are trade-offs. This is a give and take situation. You don't get anything for free. There's no such thing as a free lunch, right? Same thing here. I'm using 1 pound of force, but I have to be trading something off. What I'm trading off is the distance that it's traveling. Notice, if I have a 1-to-1 system, the distance that I'm traveling is equal to the same system that I'm putting in. This one, I'm getting 4 times less effort force in, but I'm going 4 times the distance. Right? Now, it depends on the situation you want, but usually these systems are designed to increase the force that we're applying. Okay? I can't turn a screw by my hand, so I use an inclined plane, technically is what a screw is. I use that to increase the force that I'm using, okay, with the screwdriver. There's no way I could turn that by hand, but once I use the screw simple machine, then it creates an easier or more explosive version of my effort force. Oops. So, We have the magnitude force. The magnitude of force is just the size of the force. How much? Like 1 pound is the magnitude. Okay. The effort force magnitude is 4 times less. We talked about that. Distance traveled by the force is 4 times greater. So if we look here, this is a really fancy way of saying that the force applied in the parallel direction of my distance is how I figure out the work. Now the work is done by multiplying how much force I use. So let's say I'm using 2 pounds, and I go over, so let's say I'm using 2 pounds, and I'm pushing it parallel to, let's say, 3 feet. Okay? The work is done by simply just multiplying those together. So let's say I have a chair on the floor, and I push that chair 3 feet using 2 pounds. How much work have I done? Well, I simply multiply those two things together, and I get 6 pounds, well, it's called foot-pounds. Okay? That's how much work was done. Notice, if I don't move any distance, I haven't done any work. And if I haven't applied any force, I haven't done any work. So if this is 0, how much work have I done? 0 work. Or, conversely, if this is 0, how much work have I done? Well, the same is true. If I haven't moved it, I haven't done any work. If I don't apply any force, I haven't done any work. So that's how work. In our situations, work can be applied at angles if we really want to, using things called theta, but we will not be talking about that here. That is more trig-based, and we don't need to go into that for what we're doing. So for now, we will only be talking about forces applied at a parallel position to our distance traveled. That is to say that if we're pushing something across the floor, our force will be applied parallel to the floor. Okay? Excellent. So, work is the product of effort times the distance traveled by the same regardless of the system mechanical advantage. 1 is the magic number. If I have 1, then I haven't gained or lost anything. Now, what becomes interesting is when my mechanical advantage becomes greater than 1. If my proportion, that is to say the force of my resistant over my effort, ooh, I think that's backwards. I'll come back to that. That is to say if the force of the effort of my resistance is less than 1, proportionally less than the force is required to overcome the resistance greater, or the proportional greater distance is required, then, or if it's less than 1, is required to overcome the resistant force proportionally less than the distance it is required to travel. Mechanical advantage can never be 0. Okay, we'll come back to that. Ideal mechanical advantage. That is to take the distance traveled by my effort force, that's me pushing, okay, over the distance traveled by my resistant force. That is how far it actually moved in space. So let's go back to this. My effort force, this little red arrow, has traveled 4 times longer, right? 4 units longer than my resistant force. This has moved straight up 1 unit. For every 4 units, my effort force, this is effort, has traveled. And this is resistant. Okay? So, the amount that I am pushing, so I am traveling along the ramp. So this is the ramp, this is me, and I'm traveling. Hey, look, I'm traveling. Woohoo! Okay, and I'm traveling this way. This is effort. Now, the box that I'm holding has really only traveled straight up, right? That's all we have to think about. It traveled straight up, okay? So our ideal mechanical advantage in a perfect world is our distance of the effort force divided by the distance of the resistant force, or how much the package weighs, okay? Actual mechanical advantage is a little bit different. This is going to measure our resistant force over the effort force. So this is measuring exactly how much force I use to push my box versus how much the force the actual box weighs. Notice that my ideal does not have any actual forces in it. It's only distance. And my actual has measuring the forces actually in the system. Now, your question at the end of this is going to be exactly which one is going to be bigger. One will always be bigger, and we'll talk about that in a second. But which one will be bigger? Okay, I'm going to have you answer that at the end of this as an exit ticket. Okay, so one of these is going to be bigger. Is it going to be my IMA or my AMA? Okay, one will always be bigger. Is it going to be the ideal mechanical advantage or the actual mechanical advantage? And why is one bigger than the other? If one's bigger than the other, then we must be losing energy somewhere. Okay, why are we losing energy? So that's going to be your question in a moment. Okay, we'll come back to this. All right, now let's talk about levers. Okay, so levers are just rigid bars that move effort force to resistant force. So there are three different classes of levers. There's a first class lever, a second class lever, and a third class lever. The first class lever is just like a seesaw. The fulcrum, or the pivot point, is in the middle between the effort and the resistant force. Okay? And the distance between the effort and the resistant force to the fulcrum determines its mechanical advantage. Okay? The second class lever is a little bit different. Now we have our resistant force in between the effort force and the fulcrum. That is a second class lever. Can you think of any possible scenarios that exist as second class levers? We put the resistance in the middle of our fulcrum and our effort. You're right. The wheelbarrow. Good job, guys. I'm really proud of you. I heard everyone say it. It was really cool. The wheelbarrow has the bucket, has a wheel, and has a handle. In the bucket goes the weight. Okay? The wheel acts as the fulcrum, and my effort is pushing up on the handle. So, since this has a mechanical advantage greater than 1, is this making life easier or harder on myself? Well, the wheelbarrow is designed to make my life easier. I couldn't carry 500 pounds straight up and walking across the distance, but if I use a second class lever, that 500 pounds becomes less for me to push. That second class lever will always have a mechanical advantage greater than 1. Which mechanical advantage is greater than 1? Make my life easier. But notice, if I was to use simple, logic, what travels farther? The resistant force moving up and down here, or the effort force moving up and down further away from the system? If you look at here, this line indicates where this is traveled. Hold on, let's get this. Okay, while simultaneously this line indicates where my effort force. Which one is longer? That's right, the effort force is. Remember, if I'm making my life easier with how much force I have to put in the system, I'm losing out on the distance I have to travel, which means the distance I have to move will be greater. Finally, the third class lever is the exact opposite of the second class lever. The resistant force is on the end, with the fulcrum, leaving the effort force in the middle. Now, you're right. Since the second class lever had the opposite scenario, and that mechanical advantage is always greater than 1, this third class lever, since it's the opposite, must have a mechanical advantage less than 1. Congratulations. You solved it. Why on earth would I ever want to make my life harder? Because if my mechanical advantage is less than 1, then I must be using more effort than I'm getting out on resistance. But notice I'm also traveling less distance. So why on earth would I want to do that? Can you think of any scenarios in which exist a second class lever that we use? I mean, I use almost every day. Wait for a second. You're right. The stapler. 100% correct. Good job, guys. My effort goes here, and that's my effort, and my resistant is here on the stapler. Thank you for commenting on my stapling drawing there, Nathan. I appreciate that. Ailey, I hear you laughing in the corner. Harrison, wake up. Nilo, you're doing great, buddy. All right. So when I push down here, more effort goes there. Coolio? Excellent. That's it. That is going to take our lesson for today. Tomorrow, or on Friday, I'll talk about moments, which is actually calculating work, but in a circular way, because I can't talk about work anymore if my lever is moving clockwise and counterclockwise. So we'll talk about that starting on Friday. But for now, your assignment is posted at the end of this video, and you must upload that to get credit for today.